Hello everyone and welcome to this presentation on problem Bitwise XOR of all pairings. In this session, I will walk you through the solution approach, algorithm and code implementation in C++. Let's get started. To begin, let's understand the problem. The input consists of two integer arrays nums1 and nums2. Our task is to compute the XOR of all pairings between elements of these arrays. A pairing involves taking an element from nums1 and another from nums2 and calculating their bitwise XOR. The goal is to find the cumulative XOR of all such pairings. Next, let's focus on optimizing the solution. Instead of brute forcing through all pairings, we use the properties of XOR. XOR is both commutative and associative, meaning the order of operation doesn't matter. This allows us to simplify the problem by pre-computing the XOR for each array separately. These pre-computed results, XOR1 and XOR2, represents the XOR of all elements in nums1 and nums2 respectively. The next insight involves leveraging the lengths of the arrays. If the size of nums1 is odd, each element in nums2 contributes to the final result. Similarly, if the size of nums2 is odd, each element in nums1 contributes. This observation drastically reduces unnecessary computations. Ultimately, we combine contributions from XOR1 and XOR2 based on these conditions to obtain the final result. Let's break down the algorithm into simple steps. First, we initialize two variables XOR1 and XOR2 to 0. Then we calculate the XOR for all elements in nums1 and store it in XOR1. We do the same for nums2 and store it in XOR2. We check the sizes of both arrays. If size of nums1 is odd, include XOR2 in the result. If the size of nums2 is odd, include XOR1 in the result. Finally, return the computed XOR as the result. Here's the C++ implementation of the solution. The XOR all nums function begins by initializing XOR1 and XOR2. We iterate through nums1 to calculate XOR1 and through nums2 to calculate XOR2. Depending on the sizes of the arrays, we conditionally include XOR1 and XOR2 in the final result. This efficient solution avoids brute force computation of all pairings and works in linear time. Now let's analyze the complexity of this solution. The time complexity is big O of n plus m, where n is the size of nums1 and m is the size of nums2. This is because we iterate through each array once. The space complexity is big O of 1, as the algorithm uses a constant amount of memory irrespective of the input size. Let's walk through an example. Suppose nums1 is 2, 1, 3 and nums2 is 10, 4, 5, 6. First we compute XOR1 as 2 XOR 1 XOR 3, which equals 0. Then compute XOR2 as 10 XOR 4 XOR 5 XOR 6, which equals 3. Since the size of nums1 is odd, we include XOR2 in the result. However, the size of nums2 is even, so XOR1 is not included. The final result is 0 XOR 3, which equals 3. In conclusion, this problem highlights how we can optimize computations using the properties of XOR and array sizes. Instead of brute forcing through all pairings, we take advantage of mathematical properties to achieve an efficient solution. This approach ensures a faster runtime and minimal memory usage. That's all for the explanation. If you have any questions about the solution, the algorithm, or the code implementation, feel free to ask.